I really need some good intro music. Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Stella Ocker with us today. Hey, Stella.
Hi, how's it going?
I am doing well on this May 24th, 2021. I'm in Phoenix. Where are you at?
Oh, I'm actually in Providence, Rhode Island right now.
Oh, okay. Okay. I think the article, so you still go to school in Ithaca, right?
Yes, I do. I've just been working remotely because of the pandemic, but
Yeah.
presumably I'll be going back to Cornell to work in person there sometime soon.
Yeah, probably in the fall, because I know we're planning on going a full open in August when we start up for the fall semester. So it'll be good. So where are you on your trajectory as a grad student?
I'm currently in my third year, so I passed my master's exam this past fall, and I have about 2 years roughly left.
Mm-hmm.
So
A dissertation.
yeah,
That's awesome. Congratulations on your master's.
thank you.
Congratulations for having this first author paper in your third year as a grad student. That's just wonderful.
Thanks.
So Stella, what do you like to do for research?
So my research kind of pulls together a lot of different threads that are all connected by how we can study plasma, ionized gas in a wide variety of astrophysical contexts, largely by using radio wave propagation. So I study how pulsars can be used to map the distribution of plasma in the galactic ISM. I study how fast radio bursts can be used to probe ionized gas from all the way from their host galaxies through the intergalactic medium to our own Milky Way. And I also study the galactic ISM in a context that's much closer to home. I actually am part of the Voyager interstellar mission, and we use the Voyager spacecraft to study plasma just outside of the solar system. So
Very
it's
cool.
a wide variety of threads, all tied together by gas, basically.
And mapping.
Yes.
Very cool. Very cool. And that is going to bring us to this very lovely APJ article on constraining galaxy halos from the dispersion and scattering of fast radio bursts and pulsars. And Stella, take us away.
Sure. So this paper, broadly speaking, is really focusing on how we can leverage the propagation effects experienced by both fast radio bursts and pulsar radio emission to probe ionized gas in a wide variety of contexts, but more specifically in this paper in galaxy halos. So we're specifically interested in leveraging the propagation of both pulsar emission and fast radio bursts to try to constrain the properties of the hot diffuse gas that's in the Milky Way halo, and also for some FRBs to try to constrain the properties of gas in the halos of other galaxies. And this really requires taking advantage of both scattering of FRB emission and also dispersion. And so scattering and dispersion are the two main propagation effects that we're trying to tie together to probe the properties of specifically density fluctuations in ionized gas along FRB lines of sight. So broadly speaking, this gets into a big issue that's talked about a lot in FRB studies, which is the so-called DM budget. There's this issue of how much of an FRB dispersion measure, or DM, which is the integrated electron density along the line of sight, how much of an FRB DM is contributed by gas in the FRB's host galaxy, how much of the DM is contributed by the intergalactic medium, and how much of the DM is contributed by the Milky Way. And we care about this because FRB dispersion measure is a really useful tool for probing the properties of that gas. And in particular, people are really interested in constraining the cosmic baryon density, the density of the IgM,
Yep.
which is of big interest for cosmology, and FRB's DMs can be used to probe that intergalactic cosmic baryon density. But in order to do that, you need to understand how much DM is actually contributed by the IgM.
Right.
So that's a big issue. But in this paper, we're kind of trying to present how it's not just the FRB DM budget that matters, it's also the scattering budget. It's how much of the observed FRB scattering is contributed by different media along the line of sight, because dispersion and scattering, they really go together. So I suppose probably the best place to go now is to go down to equation 1, I think.
Okay. There we go. Electron density fluctuations and scattering.
Okay, so scattering of FRBs and of compact radio sources in general can be broken up into a few main effects, but the effect that is most important to talk about for this paper is pulse broadening, which is where you basically have the characteristic time delay that the burst experiences as it is scattered by density fluctuations in gas along the line of sight. And so what you end up seeing is that scattered rays of the burst will have different propagation paths through gas along the line of sight. And so some of those propagation paths will take longer than the most direct, like straight line of sight to the source. Mm-hmm. So what you end up seeing is that if you have a profile of a burst, and you might imagine that a typical simple burst might look just like a Gaussian. But if you have scattered rays, then you'll actually end up having like a broadened burst where you see this kind of long tail to the burst profile that comes from the rays that traveled the longer path lengths, essentially. Okay. And so we characterize that temporal delay that's experienced by the scattered rays using this time delay tau in equation 1. So tau is like the characteristic time delay that's experienced by a scattered burst. And that time delay is actually directly related to the dispersion measure DM. And it's related to the DM contributed by the gas that the burst is traveling through. But it's weighted by some other factors. And those main factors are F tilde in this equation and G scat. So F tilde is what we call the fluctuation parameter. Okay. And so the fluctuation parameter essentially describes the statistical properties of density fluctuations in the gas. Mm-hmm. And so it's related to things like the outer and inner scale of turbulence, which dictates what the wave number spectrum of density fluctuations in the gas looks like. Right. So F tilde, the fluctuation parameter, is kind of like our compact way of describing what the properties of the density fluctuation in the gas are like. Mm-hmm. And then that's also weighted by this geometric factor called G scat. So this G scat essentially describes how the relative geometric configuration of your source, your scattering lens of material, and the observer will impact how much scattering you actually end up seeing. And so G-scat depends on the relative distances to the source, the scattering layer, or the lens, and the observer.
Okay, I'm with you.
So, so those are the main factors that kind of determine how scattering and dispersion are related in this very simplistic way. And it's important to note that the scattering time tau is measurable, as is the dispersion measure. And so these are directly observable quantities that we can then, in a very straightforward way, relate to the fluctuation parameter. And we also can measure G-scat by measuring the redshifts of the host galaxy, for example. And if we have, say, an intervening galaxy that's acting as our lens, then we can have the redshift to that intervening galaxy lens, and so on. So that's how we can tie together and disentangle these different factors.
Cool.
So that's kind of the overview theoretical background. And so what we're doing in this paper is we're leveraging measurements of scattering time, tau, and dm to try to constrain the fluctuation parameter, f tilde, for the Milky Way halo and for some other galaxy halos that intervene lines of sight to FRBs.
Okay. Nice.
So first, we can talk about how we do that for the Milky Way halo. So if you scroll down to, let's do figure 1.
Okay.
All right. So to constrain the fluctuation parameter of the Milky Way halo, we need to know something about how much the Milky Way halo contributes to FRB DMs. And this is actually a somewhat contentious and very well-studied topic, how much DM the Milky Way halo contributes to FRBs. And there are kind of a few different models for it, but all of these models operate really under the assumption that the Milky Way halo, the hot diffuse gas in the halo, contributes a small but non-negligible contribution to FRB DMs, and that DM contribution is somewhere around 50 parsecs per cubic centimeter. But the exact quantity depends on how the model represents the density profile of the halo, essentially.
Mm-hmm.
And so in this paper, we're using a specific model that was developed by Prochaska and Zhang from 2019. Mm-hmm. And the density profile for this model is shown in the bottom panel. So essentially, this model takes the classic NFW profile for a dark matter halo, and it adjusts it with a roll-off at the galactic center. So that's essentially to avoid this kind of sharp cusp that you would normally see in the NFW profile.
Okay. Mm-hmm.
And so we adopt this model for the density profile of the Milky Way halo and also for the other galaxy halos that we consider. And you can get a DM estimate from this model by integrating over the electron density along the line of sight. And so that integrated electron density, the DM contribution, is shown in that top panel. And so you can see it asymptotes at about 60 parsecs per cubic centimeter. And also, just a very quick side note is that the blue curve is just showing our specific numerical implementation of this model. We just wanted to have a more physical roll-off to the model when we were integrating over it, but it doesn't really affect the DM prediction of the model per se.
Right.
So that's how we basically model the DM contribution for the Milky Way halo, but now we get to the other factor that we need to consider, which is the scattering. And so here things get a little bit more complicated. So essentially, to constrain the scattering contribution from the galactic halo, if you scroll down to equation 5, probably.
5, 6, 7.
Yeah, so to constrain the scattering contribution of the galactic halo, we essentially need to deconstruct the scattering that's observed from an FRB, for example, because an FRB is an extragalactic source. The scattering it experiences will be contributed not only by the halo, but also by the disk of our galaxy. And so what we essentially do is we say, let's assume that the total scattering we observe from a given FRB is just the sum of scattering that's contributed by the galactic disk and scattering that's contributed by the halo. And then we can disentangle the scattering contribution of the halo using our understanding of the galactic disk from pulsars. And so the galactic pulsar population gives us some good constraints on how much scattering happens in the galactic disk. And so using that knowledge, we can subtract out how much scattering comes from the disk and get scattering from the halo.
Okay.
And equation 6 is just showing an additional scattering measurement called the angular broadening. That's another kind of scattering measurement that we use. So if you scroll down to figure 2, this figure is showing the distribution of pulsar scattering times divided by their dm squared for all galactic pulsars.
Okay.
So this blue band is showing the values that correspond to pulsars above plus or minus 20 degrees galactic latitude. And so those pulsar lines of sight predominantly trace the warm ionized medium in the thick disk of the galaxy. And then on the right-hand axis, we have the equivalent values for the fluctuation parameter, right? Because pulse broadening time, scattering time divided by dm squared is directly related to the fluctuation parameter.
Right, from equation 1. I'm with you.
Yeah. And so there are a few things to note in this plot. One of them is with this distribution of tau over dm squared for pulsars, we get a direct constraint on the fluctuation parameter for the thick disk. And we also get a constraint on how much scattering happens in the thick disk. Another thing that we get is that you can see that the fluctuation parameter increases dramatically as you go to lower galactic latitudes. And in particular, for lines of sight that are closer to the galactic center, which are highlighted in orange. And so this helps illustrate the physical characteristics of the fluctuation parameter, because you'd expect that as you look down closer to the galactic plane and towards the inner galaxy, you'll see a much larger fluctuation parameter because the gas is much denser, you have more H2 regions, much stronger density fluctuations. And so there's this direct physical connection between the structure of the gas in different regions of the galaxy and the value of the fluctuation parameter.
Okay, cool.
Okay, so let's see. Do you mind zooming out again?
I do not.
Okay, thanks. Okay, so now another thing that we can do to constrain the amount of scattering that comes from the galactic disk is we can use this galactic electron density model called NE2001. And so NE2001 is this very widely used model for the distribution of free electrons in the galaxy. It was actually developed by my advisor, and using NE2001, which is based on constraints, observed constraints from the galactic pulsar population, we can also make predictions for how much scattering is contributed for any given line of sight through the galaxy. So that's another tool that we can use to constrain the amount of scattering from the galactic disk. So using these two tools, that are based on galactic pulsars, we then look at two specific FRBs to make some statements about how much scattering happens in the galactic halo. And so those two FRBs are FRB 121102 and FRB 180916. So FRB 121102 is very famous because it was the first repeating FRB to be discovered. And it also is very well studied and has a very large set of scattering constraints. So it has an array of scattering measurements that have been made at different observing frequencies. And so this allows us to make some very strong constraints on the scattering for this FRB's line of sight. And so figure 3 is showing several different measurements of the scintillation bandwidth, which is a specific scattering measurement that's directly related to the scattering time.
Yes.
And these are taken from a variety of different studies. And so this just demonstrates how using this array of scattering measurements from different studies, we can make a strong constraint on the average scattering that's occurring along this line of sight. Mm-hmm. And then in figure 4, we can see that the scattering along this line of sight is likely dominated in large part by the outer spiral arm of the galaxy. So what this plot is showing is the electron density dm and cn squared, which is essentially the strength of turbulence along the line of sight to this FRB, as predicted by the NE 2001 model.
Okay.
And so these spikes, not spikes, more like bumps you see in the density and cn squared, those are from the outer spiral arm, which is about 2 kiloparsecs away.
Okay.
And so this gray band is then showing what the predicted, well, not predicted, sorry. This gray band is showing the distance to the dominant scattering material for this FRB. So to explain that further, we'll need to go down to figure, I've lost count of which figure we're on. Figure 5.
We're on 4, so we'll slide down to 5. Nice table 1 there on those 2 FRBs. And figure 5 is the distance to the scattering region. Slightly smaller, there we go. Okay.
Yeah, so we can actually estimate the distance to the gas that's responsible for scattering this FRB because we have both an angular broadening measurement and a scintillation bandwidth measurement. And so using these 2 different kinds of scattering measurements are directly related to each other by the distance to the scattering region.
Yes.
And so this plot is showing how the scattering diameter relates to the distance to the scattering region. The green band is showing the angular broadening predicted by the scintillation bandwidth measurement. And then the blue band is showing an independent direct measurement of the angular broadening from another study. And so the overlap of these 2 things gives you the distance to the scattering region. And so you can see that it falls right around 2 kiloparsecs, which is consistent with the distance to the outer spiral arm.
Yep.
And so putting all of this information together more concisely, we can say that for FRB 121102, the scattering along this line of sight is really dominated by the galactic disk and more specifically by the outer spiral arm.
Nice.
And so we really don't expect much scattering at all from the galactic halo. And so this means that we can actually use this FRB to place an upper limit on the amount of scattering happening in the galactic halo.
Yes. Okay,
so to skip over some details, we essentially do a similar kind of analysis for FRB 180916, which is another well-studied FRB. It has some good scattering measurements. So we can do a similar kind of thing. And then what we essentially do is we combine the constraints from both FRB 180916 and FRB 121102 to make a joint constraint on the amount of scattering from the galactic halo. So that's in section 3.3. And so what we essentially do is first we take the scattering constraints and we place an upper limit on the product of the fluctuation parameter and the dm for the galactic halo.
Okay.
And then using our model for the DM contribution of the galactic halo, we then disentangle our upper limit on the fluctuation parameter.
Yep, I'm with you.
Okay. So before we go and actually talk about the value of the fluctuation parameter for the Milky Way halo, I think it's better if we first talk about some of the other lines of sight to FRBs that we discuss.
Okay.
And then that'll help us kind of tie it all together into a cohesive picture. So the other thing that we do is we look at two other FRBs, FRB 181112 and FRB 191108. These call numbers probably are not very significant to anyone. But anyway, these two FRBs are interesting because they both have other galaxy halos in between our galaxy and their host galaxies. So FRB 181112 and FRB 191108 also have scattering measurements. And so basically, by combining their scattering measurements with models for the DM contributions of those intervening galaxy halos,
yes,
we can place constraints on the fluctuation parameters of those intervening galaxy halos. So let's skip all the way down to the last figure.
Ah, there they are. Okay, got it. I was a little slow there. Okay.
So this figure is essentially tying together all of our different constraints on the fluctuation parameter for different lines of sight. And so the Milky Way halo value shows us our upper limit on the fluctuation parameter for the Milky Way halo. Yes. Then we have upper limits on the fluctuation parameters for the halos intervening the lines of sight to those two other FRBs. So one of those is FRB 181112, and so its intervening galaxy halo has, you know, the shorthand, essentially foreground 181112, and then FRB 191108 actually passes through the M33 halo, and so this upper limit is actually for the M33 halo along the line of sight to FRB 191108. Now, there are also some other values on here for the Milky Way, and we also have, so we have our constraint on the fluctuation parameter for the thick disk of the galaxy. That's based on the galactic pulsar population, that figure 2, I think it was. Yes. And then we also have values of the fluctuation parameter that are characteristic for lines of sight to the Milky Way anti-center and for lines of sight towards the inner galaxy. Okay. And then we also have an estimate of the fluctuation parameter for the Large Magellanic Cloud that's based on a single pulsar, pulsar B0540 minus something. Okay. That's one of the pulsars that is located in the LMC and is the only LMC pulsar that actually has a scattering measurement. And so using that single scattering measurement combined with the DM, we can place a constraint on F tilde for the LMC. Okay, so now that I've described where all of these different measurements come from, let's talk about what the actual physical meaning of this plot is. Okay. So there are a few things to notice. The first being that the fluctuation parameter is largest in the Milky Way inner galaxy and the LMC. Yep. And so I explained earlier how it makes sense for the fluctuation parameter to be very large towards the inner galaxy because the ISM there is so much more dense. There's more H2 regions, more star formation. Basically, just all the fun stuff is happening in the inner galaxy. And then in the LMC, the fluctuation parameter is actually very large for that line of sight because the pulsar that we're using is actually associated with a supernova remnant. And so a supernova remnant can act as an enhanced scattering region. You see enhanced density fluctuations there. And so that's why those two values of the fluctuation parameter in the inner galaxy and the LMC are so large.
Okay, good.
Now, the other thing is that by the same reasoning, you can see why the fluctuation parameter is much smaller towards the Milky Way anticenter and even smaller in the galactic thick disk. This generally just traces where the gas in the galaxy is, has more going on in it, basically. Now, that being said, it's actually somewhat surprising that our constraint on the Milky Way halo fluctuation parameter actually allows the Milky Way fluctuation parameter to be larger than that in the thick disk.
Yep.
Because broadly speaking, our current picture of the Milky Way, based on many different kinds of observational constraints, leads us to expect that the thick disk is dominated by warm ionized gas. That's gas with a temperature of around 10 to the 4 Kelvin, while the Milky Way halo is largely dominated, the baryonic matter in the Milky Way halo is largely dominated by hot diffuse gas. That's gas with a temperature of around 10 to the 6 Kelvin, with a much larger filling factor. And so based on that physical picture, we'd actually expect the fluctuation parameter to be larger in the thick disk, larger in the warm ionized medium than in the Milky Way halo or in the hot ionized medium.
Okay.
So how do we then interpret the fact that our upper limit for the halo falls above our constraint on the thick disk? Well, we don't make too much of it, largely because our constraint on the fluctuation parameter for the galactic halo is only based on 2 FRBs, right? And so obviously we're not doing the best kind of constraint that we can, yet. So what that indicates is that this constraint on the fluctuation parameter for the Milky Way halo is not really constraining enough to make any more kind of specific statements about the properties of the gas in the halo, at least based on the value of F tilde. Now, the other thing to note is that our values of F tilde for the other intervening galaxy halos are very small. They're smaller than our constraint on the thick disk, and they're smaller than our constraint for the Milky Way halo.
Yep.
And for both of those FRB lines of sight, we see that very little scattering is happening in those intervening galaxy halos. So based on that, we don't see much evidence for a lot of scattering happening in intervening galaxy halos, at least for the FRBs that we consider here.
Right.
So that kind of ties together like the big conclusions of the paper. So I should probably stop and let you ask anything if you have any questions.
That's great. Thank you very much for walking us through this really lovely paper. But you end on a great point. And so you kind of allude to it. So where do we go over the next 5 years, let's say, in this mapping adventure? Are there more FRBs that one can do this line of sight analysis, and you don't have to spill your thesis if you don't want to? Is there more data coming where one could apply this analysis, and so on? So just sort of where do we go over the next 5 years, given what you've published here?
Absolutely. So as I'm sure you're aware, FRBs are a rapidly growing field, and there are a lot of really exciting FRB surveys happening right now that are in the process of vastly expanding our sample of known FRBs. So one in particular is CHIME, the Canadian Hydrogen Intensity Mapping Experiment, which also actually surveys FRBs.
Yes.
And so CHIME is expected to find thousands of FRBs every year of its operation. Indeed, it's found many new FRBs already. And so one of the most natural next steps of this analysis is to just apply it to a much larger sample of FRBs. And so I would say, like, my attitude towards this paper is that it's really kind of trying to like lay the first step
Right.
for us to move forward, and really like apply this methodology to a much larger sample.
Cool.
And there are already some FRBs that have been discovered that will be very interesting to apply this analysis to. Just a couple of months ago, an FRB was published that's in the Galaxy M81, and so it's a very nearby FRB, and it'll be really interesting to apply this analysis to its scattering measurements and see what happens.
Very nice.
So, and there will probably be more sources like that too. And I think something that we haven't actually found yet, but would be interesting to find, would be an FRB with an intervening galaxy halo and a large amount of scattering, because we haven't yet seen the scenario that's maybe sometimes expected, which is that, oh, if we have an FRB with an intervening galaxy, then we'll see a ton of scattering. And we haven't actually seen that scenario yet, so it'd be interesting if we did one day. But yeah, that's kind of the major next steps.
Cool. I'd say you're probably going to have a very interesting thesis over the next couple of years. Lots of activity going on in this, and then probably beyond your thesis as more and more data comes in and you do this kind of analysis. So it's really great. So Stella, thank you once again for walking us through these opening steps of mapping with FRBs and pulsars.
Yeah, thank you so much for having me. It was fun.
All right, everyone, thank you so much, and we will see you on the next one. Bye-bye.